Hey folks, Ms. Gosling here. In this video, you're going to learn about Sankey diagrams. By the end of the video, you'll be able to analyze and create Sankey diagrams. Now let's start by actually talking about what a Sankey diagram is. So a Sankey diagram is essentially a graphic representation of our efficiency. And one thing that's really cool about our Sankey diagrams is they show us where exactly the lost energy goes. So for example, in this Sankey diagram pictured on the slide, we have a bunch of energy being input. Some of that energy is lost to smoke, to a condenser, to friction, to the alternator. And then you can see that only a small portion of that energy is actually output into useful energy. So when we draw a Sankey diagram, what we want to do is we want to use the width of our arrows here to scale, to use as a scale to represent energy transfers. So we have our whole energy input, and the width of that arrow should be equal to the sum of the widths of every single other output energy, including the useful energy and the wasted energy. So if we have any energy that's being wasted, we're going to point those arrows down to show that it's not being used as useful energy output. And again, the width of the arrow represents the amount of energy that's lost. And then finally, pointing to the right, we have our useful energy. And again, the width of that arrow represents the amount of useful energy. Now, one other key thing, guys, is that the length of our arrows is not important. It does not matter. The only thing that matters here is the width of my arrows. So let's go ahead and look at an example of a Sankey diagram. So the Sankey diagram to the right here shows the distribution of energy in a light bulb. What is the efficiency of the bulb? So you can see here, my Sankey diagram has a width of 100 joules. Down here, I have a line width of that is 9. So say that this is 10 squares in my graph. The width of this arrow here should be about 9 squares. And the width of this arrow here will be 1 square to represent 100, 90, and 10. So we know from our Sankey diagram that the energy input is the energy that is listed here. It's the width of our initial arrow. So my energy input is 100 joules. I also can see that my output here is labeled as light energy and has a width that represents 10 joules of energy. Thus, my unknown is eta, the efficiency of my light bulb. So I know that my equation for eta is given by eta equals out over in times 100. Thus, when I sub and solve, I get that eta is equal to 10 over 100 times 100. Thus, my light bulb is 10% efficient. So moving on to example 2. An electric motor is a device that transfers electrical energy into kinetic energy. 60 joules out of every 90 joules supplied are transformed into kinetic energy. 30 joules are degraded as heat and as sound. Draw the Sankey diagram for this motor and use that diagram to calculate the motor's efficiency. So let's start by drawing my diagram. And I have some graph paper here on the right that should hopefully help us in doing so. So I know that so what I'm going to do is I'm going to say 2 squares equals 10 joules, or 1 square equals 5 joules. So if I have 90 joules coming in, then my input must be 18 squares. So let's go ahead and do that. 5, 10, 20, 30, 40, 50, 60, 70, 80, 90 joules are being supplied. And I'm going to go ahead and just give myself a little width here to work with. So I know that 30 joules are degraded as heat. So let's go ahead and do that on the bottom. 10, 20, 30 joules are degraded as heat. So let me go ahead, let me represent that slightly better. So let's draw an arrow this way, and we know that we have 10, 20, 30 joules being degraded as heat. So I'll go ahead and draw that arrow down here. Next, I know that 60 of the joules in my energy are useful. They're transformed into kinetic energy, which is what I was hoping to get. So let's go ahead and do that. 10, 20, 30, 40, 50, 60 joules are transformed into useful energy. So let me go ahead and again, I'm going to represent that with my arrow here. And then drawing backwards, here we go. Connecting my dots, I have my Sankey diagram. Now the last thing I want to do is I want to go ahead and write what each part is. So here we have this labeled as heat and sound, and pointing off to the right we have our kinetic energy, and input we have electricity, so electric energy. So now that I have my Sankey diagram drawn, I can go ahead and I can do my calculations. And I'm not going to go through the guess method, I'm just going to go ahead and do it. So I know that eta is equal to energy out over energy in times 100. My energy out is 60 joules. My energy in is 90 joules times 100. So exactly 2/3 of my energy is being transformed. Thus my efficiency is approximately 67%. So let's go ahead and talk takeaways. First, Sankey diagrams graphically represent the efficiency of an energy conversion. The width of an arrow in a Sankey diagram represents how much energy goes into a specific process. And in a Sankey diagram, arrows representing wasted energy point down, while arrows representing useful energy point to the right. So now you guys know how to draw and interpret and use Sankey diagrams to calculate efficiency. So it is your turn to try creating some Sankey diagrams on your own. Best of luck and happy solving!